OTA, well, he studied in Scarborough and he was there, he should be in Scarborough and he didn't read the pieces. Another one, neutral announcement is, well, on the final exam you'll have all the material that we covered up to last lecture, I mean including Gaussian integers, but not including RSA, not including Bell's equation, but including everything else. So this information is posted on the course website on small margins. Well, third announcement for everyone, I got some cookies, just well, become for material which is not going to be on the exam, so please, well, you should get some bonus. Well, so another bonus is we can actually discuss whatever we want and we like, and I wanted to discuss such a question. Well, we know how the last digits of powers of 2 are distributed. If you look at this list, these are powers of 2, and we know that, well, there is some list of them, 1, 2, 4, 8, 6, and then once again 2, 4, 8, 6, 2, 4, 8, 6, 2, 4, 8, 6, and so on. So they start repeating the last digits. If you look at this list, it seems that the first digits also start repeating. 1, 2, 4, 8, 1, 3, 6, 1, 2, 5, and then 1, 2, 4, 8, 1, 3, 6, 1, 12, 2, 5, maybe. But it turns out that, well, they don't. If you try, if you more, you'll find that this list doesn't repeat, it doesn't have any periodicity. And you'll find out that, well, in this list, there aren't any numbers which start with 7, there aren't any numbers which start with a 9. The initial question is there some power of 2 which starts with a 7? Is there some power of 2 which starts with a 9? And it turns out that, well, you'll have to keep computing powers of 2, and, well, it's really not that obvious that you are going to find some power which does start with a 9. So let's think a little bit about what is the actual meaning of this question. What does it mean that some power of 2, 2 to the power n, starts with a 9? Well, it means that this number is between 9 something 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 and 1 something something something. It means that this number is between 9 times 10 to some power and 10 to the next power, like this. So if this inequality is ever satisfied, then you know that this power of 2 has first digit, which is 9. So 2 to the n starts with 9. And only if this inequality holds. Well, that's kind of obvious. These are all the numbers which start with a 9, they are all the numbers between these two. Well, just the way to rewrite this equation, and it doesn't seem to, well, it's just a way to rewrite the same equation, it doesn't seem to help. Well, it does help if you take the logarithm. You know that the logarithm takes a power and changes it into a product. So here you have product of power of 2. If you take the logarithm, you're going to get something with just products. And the most convenient logarithm is logarithm to base 10. Because then, let's see what we have. Let's take logarithm to base 10 of all the terms. So we want this equation to be satisfied, and we can easily rewrite it. It's k plus logarithm of 9 to the base 10 is smaller or equal than n times logarithm of 2 to the base 10, which is smaller than logarithm smaller than k plus 1. So instead of computing powers of 2, you can compute multiples of logarithms. Well, that's helping a little bit, but not very much. I mean, if you want to know precisely what is this n times logarithm of 2, you have to actually compute logarithm of 2 to the base 10, which is not an easy task. Well, we have still to verify such inequalities. Well, one observation. Here, it should be a number between k plus some number between 0 and 1. This number, well, you should raise 10 to the power between 0 and 1 to get 9. So this number is a number between 0 and 1. It's 0 point something. And k plus 1. So what's written here is that actually it should be between an integer plot, integer dot something, and the next integer. It means just inequality of the fractional part of n takes logarithm of 2. So if this is the fractional part, kind of take the fractional part of 0.8. So this inequality means just this thing. The fractional part of this number is between 1 and this funny number. So, well,
it's a log 2 based on that.
Sorry?
Wouldn't that be log 2 based on that?
Okay, then, oh, yes, of course. So, what happens here? I started with the question of whether the power of 2 starts with a 9. I end up with the question of whether such a number, the multiple of this funny number log of 2 to the power to the base 10, ever has a fractional part between this number and 1. So this number is something like 0.9. So is the fractional part of this number ever between 0.9 and 1? Let me reinterpret this question a little bit. What does it mean that I'm taking the fractional part? Let me imagine a circle of total length 1 and imagine that I'm making steps of length this number. So let me denote by x this number, logarithm 2 to base 10. And what I'm doing is as follows. Here is 0, and then I'm going, I'm making one step of length x, another step of length x, another step of length x. I'm making n such steps. Every time I make an integer number of terms, I just forget about the integer part. I don't care about how many terms I make, only about what is the distance from 0. So I can keep doing this. I might get some numbers like this. And eventually I want to get somewhere close into this region. Between, so this is logarithm 9 over 10. And I want to get eventually to this region. It's just another interpretation. I'm making steps of length x along the circle, and the question is, will I ever land inside of this small interval? So, was this part clear enough? How many of you did not understand why this question is equivalent to this question? Okay, so what step is the most confusing? The algebraic manipulation? Okay, sir. So the reason is because I'm concerned about the, well, if it was just like this, then I would be doing the following. I'm taking a line and I'm making jumps of length x. 1x, 2x, 3x, 4x, and so on. Right? But I'm not actually concerned about the actual number. I'm only concerned with the fractional part. So every time I make, well, here it's 0, here it's 1. Once I make a step beyond 1, well, I don't want to continue here. I want to pretend that I actually continue here. So at the point 1, I make a cut, and I connect it to the point 0. And now I'm making the jumps along a circle. The length of the circle is 1. And as you see from this list, I'm actually, well, at least in the first 2 iterations, I'm skipping this interval. So the picture there is somewhat like this. I have some interval in which I want to get, maybe it's a short interval, something like this. Then the first 2 iterations look like this. Well, maybe 0, then I make a jump, 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 and well, I overshoot it. Then I make another sequence of jumps. Well, and once again, I overshoot this interval somehow. And the question is, will I ever land inside of this interval, or will I always overshoot? So we started with this question about numbers. Now we are talking about kind of geometrical question of will we always overshoot this interval, or will we ever land inside? And the thing is that this question has very simple and very general answer. So maybe somebody knows the answer, or maybe yes.
Yes, it will definitely land inside.
Mm-hmm. So can you tell for what numbers x, for what lengths x will then always land inside? No. Yeah? Irrational, yes. So it turns out that whenever you choose a step which is irrational, you will always get as close to any point as you wish. So say you want to get inside of this interval, well, if x is irrational, if your step is irrational, you will be there. If you want to get to any other point as close to, say, this point, random point here, as you wish, you will be there eventually. You might have to make lots of steps, but eventually you will land there. And, well, it is important for the steps to be irrational. If it is a rational number, then you will be jumping along the vertices of a regular endpoint. And then, well, of course, you can choose some interval which is not between 2 points or 2 consecutive vertices of the endpoint. But if x is irrational, then you have a set which is what's called dense. So let me write down the statement. So take if x is irrational, then the set of such fractional parts of n times x, set of such fractional parts is dense in the open interval. Well, this dense doesn't mean that there are just too many, there are a lot of points. It has a precise technical meaning. It means for every interval that you choose inside of 0, 1, you will find at least 1 point from your set. So i.e. for any interval inside of 0, 1, or any interval inside of 0, 1, there is n side z and x, the fractional part, lies in this interval. So there is nothing particularly important about our interval from here to here. It's always for any rational step, and for any interval, however short, there will be some multiple of x that will, well, such that the fractional part of this multiple lies inside of this interval. Do you know the proof of this?
Yes.
You want to tell?
Okay, so you have x, and you go around, and then you won't, when you run around one time, you'll end up between 0 and your first x. You won't end up at 0 because it's irrational. You won't end up at x because the step won't get you far enough. And so basically, you go around once, and you'll get a length that is less than your original x. But then every time you do this, you're going around this new distance, so you can call it x1. And then you have a smaller distance, x1. And so in that way, you form a decreasing sequence of xn's. And then, again, every time it will be less than the original, and so you can make it go as small as you want.
Well, almost, because you know, I mean, there are sequences which decrease but not to zero. But yes, they're very, very close. So the idea is indeed that at some point you will have to jump into a point which is closer than the original x. So at some point, well, the first argument that he told was like this. You make a jump of x for the first time. Then you make a whole circle, and eventually you're going to be at a point such that the next jump, well, you'll make a full turn. So here you are, you make the next jump, you have to land into this interval between 0 and x. There is no choice. You can't overshoot it because the length of the jump is just x, and this is interval length x, and you adjust a little bit before this. So you land somewhere inside. Now, well, now you know that every time you make not just 1 times x, but this n times x, where n is this number of jump that lands inside of here, you'll make just one small step along the circle. Well, it's not just one step, it's the full turn plus a small step, but it doesn't matter. We're still landing at the same point. So now we can do the same trick, but with this smaller jump. Because now we can repeat multiples of the original, well, this smaller jump. And then we can keep decreasing this jump more and more and more, but let me make it a little bit more precise. So let me prove it like this. First plane, all these things are different. There are no, well, it's impossible for two such things to be the same if x is irrational. So first plane, mx is different from mx, or m is different from m. Well, that's kind of obvious. If you have that mx is the same as mx, then mx is mx for some integer, but then, well, n minus m times x is equal to k, and then x is irrational. Then x is rational. So if x is irrational, all of these things are different. You are never going to land on a point which you already visited once. Just never. So now, let me try to prove that there will be 2 points which are very, very close to each other in this process. So I'm making these steps, and let me show that there will be some 2 points which are very, very close to each other, as close as I wish. So let me fix some measure of how close I want them to be, call it epsilon. Claim there are 2 points whose distance is at most epsilon. There are n and m such that mx minus mx is between 0 and epsilon. Just very, very close. So fix some number epsilon, maybe 10 to minus 10s, or something like this, 0.0001. I will find for you 2 points of this kind, which are, well, not farther than this number. Well, indeed, I have infinitely many points. If I have infinitely many points on the circle, I claim that there must be 2 points which are very, very close. There is no way for infinitely many points all to be farther than epsilon apart from each other. Just no way. I mean, take my circle, divide it to segments of length which is smaller than the epsilon. And now I put infinitely many points inside of this circle. But there are only finitely many intervals like this. So one of them must contain infinitely many points from my sequence. But every time I have 2 points inside of the same set, their distance is at most epsilon. So it's obvious. It obviously follows from the fact that there are just infinitely many points. Okay, so once again, there are 2 points like this which are very, very close. It means that if I take n minus m x, this number is between 0 and epsilon. The fractional part of this number is very, very small. But now, well, what can I do? Here I have a number, this is 0, this is epsilon, and I have a number, well, some multiple n minus m x turns out to fall inside. Well, let me take 2 times it, 3 times it, 4 times it, and so on. I will cover my whole circle by small segments. The length of each of them will be smaller than this epsilon. So the numbers n minus m x are no more than epsilon apart from each other. And they will eventually will get back to the original point. So they cover the whole circle by points from my set, all of which are no more than epsilon apart. So if I want to find a point inside of a long enough interval, we'll just choose epsilon to be small enough. And then I'll find points inside of this interval. So once again, the idea is like this. There are infinitely many points in this set. That's the first idea. Very simple, just because x is irrational. Second idea, every time I have infinitely many points on a circle, there must be 2 points which are very, very close to each other. Well, and once I have 2 points which are very, very close to each other, I can just choose the step between them to be my new step. I can make not jumps of x, but jumps of this very small step. And of course, if I'm making very, very small jumps, I will come very close to any point that I want. So that's basically the proof. In particular, well, if I take my logarithm of 2 to the base 10, well, the first question is it rational or not rational? Maybe that's, well, maybe let's solve this question. Before this, was this clear enough? Maybe any questions about this? Okay, so logarithm of 2 to the power to the base 10. Well, if it is rational, then yes, it will have some periodicity in the first digits. If it is irrational, we'll get every digit eventually. In fact, not only every digit, every starting number. I mean, if you want some power of 2 to start with 9, 7, 8, if this number is irrational, there will be some power of 2 which starts with 9, 7, 8. Or for that matter, with any beginning that we fix. So let's check, is it rational? Let's check that it is not rational. How to prove it? Well, assume it is rational. If logarithm 2 to the base 10 is some rational number, m over n. Let's raise 10 to go to the power to this power. So we get the 2 is 10 to the power of m over n. Or we get the 2 to the power n is 10 to the power n. But that's impossible. Why is it impossible?
in majority, the multiple of 10 is always divided by 10. And in there, but the multiple of 2 always in 2, 4, 8, and then 3.
Okay, yes, that's a possible explanation. The simpler one, this, yes.
Because like 10 is like 2 times 5.
Yes.
Like 2pm times 5pm, which was left like 2p, like 2 minus m.
Well, maybe even simpler. 5 is a divisor of this and is not a divisor of that. So even simpler. So 5 divides 10 to the power m, 5 is 2 divided 2 to the power m. But both, this is a good explanation. Both these explanations are good, they're just a little bit longer. So this number is not rational. Conclusion, you can get a power of 2 which starts with a 9. So let me check in my notes. I did write a computer program that computes the powers of 2. And the first one that starts with a 9. Well, it turns out that 2 to the power 53 starts with 9, 0, 0, 7, 1, 1, so. Well, I can write it all. 3, 5, 4, 7, 0, 9. So it starts with 9. There is a power of 2 that starts with a 9. And in fact, you can find, well, if you want to find the power of 2, it starts with 9, 9, or 9, 9, 9, 9. Well, the same theorem tells you you can do it. It's just you'll have to land an even shorter interval. But still, it is possible to do this. And I did run my computer and I found that 2 to the power 485 is 998 something. If you want to start something starting with 999, well, it turns out to be much more complicated. It's 2 to the power 11,165. By the way, it's much simpler to find a power of 2 that starts with 7, or with 77, or with 777. You'll find just much smaller exponents here. Let me try to explain this phenomenon. And it's much simpler to find the power of 2 that starts with 111. It's in the thousands. So in fact, it turns out that it's much simpler to find a power of 2 that starts with small digits than to find the power of 2 that starts with large digits. There is a kind of asymmetry. It's a funny thing, and it was first discovered by an astronomer called Newcomb, and it was funny. I mean, now to calculate something, you take a calculator, you calculate whatever. But previously, you didn't have calculators, you had to use some tables, some rulers, some devices which are called not calculators. And in particular, logarithms were much used when every time you had to multiply or take a power of something, and people used huge tables of logarithms. So it's just a table with all the logarithms between 10 and 100, well, with step 0.001, something like this. So there were huge books with these logarithms. And Newcomb, he was an astronomer, he naturally, well, flipped these books and made calculations, and he found out that the first pages of these books were always much more worn out than the last pages. And the first pages, well, they contain logarithms of numbers that start with 1. The last pages contain logarithms of numbers that start with 9. Yes?
Do you think it's maybe just because everyone who started reading those books actually bored
Well, that's a good explanation, but well, nobody was reading the book. It's just numbers. Nobody can read it. You always look up some entries. just kind of database view. So, oh, well, this explanation isn't very good. He tried to find another one. And, well, initial kind of idea is that actually somehow the nature itself prefers numbers that start with 1 to numbers that start with 9. Would it possibly be true? How nature would even know that we have some system of, well, that we have 10 fingers on our hands and that we use kind of numbers to base 10 or something like this? Well, of course it can. But still, if you take any random and large enough set of data, for example, radii of asteroids and belt of asteroids, or heights of hills and mountains on theirs, or population in the cities in the, I don't know, 5,000 largest cities in the world. Always, if you tabulate these numbers, you will find much more numbers starting with 1 than numbers that start with 9. In fact, you're always going to find about 30% of the numbers start with 1, and only about 5% start with a 9. Well, it sounds kind of mysterious. But in fact it isn't. Let me explain you how it would happen.
Is that because central limit there? Because Gaussian tends to focus on at the lower end of the network.
Right? No, I'm not sure about
Okay, good talking.
I mean, no.
No.
I mean, naturally not all the data is distributed in this way. For example, if you take the heights of people in this room, well, yes, almost 100% will start with 1, and a few will start with 2, but still, I mean, none will start with 3. So it's, I mean, not every distribution, but every distribution which spans over kind of large magnitudes, where you can have some variation of order of 10, 100, 1,000. In such things, you will find this law. It's called Benford's law. And Benford was a physicist. He discovered it after Newton, and he gave an extra explanation for why it happens, maybe several explanations. Maybe any ideas? Why is it? Oh, what kind of considerations would you apply to understand how many times the number 1 to the third digit of a number taken from physics? I mean, even worse, if you take like all the mathematical constants which are interesting, like table of mathematical constants, E, pi, and all the derived versions of those, you will find that 30% of those will start with a 1, and only 5% start with a 9. Yes. Sorry? Yes, it is in fact a power law. So what happens here is that, well, how do we measure the size of an asteroid? Well, we say that here's a ruler. It turns out that this asteroid has radius of 50 centimeters. But why centimeters? Why not, I don't know, inches? Why not some other kind of scale? There is no internal link to the numbers. There is some internal link to being evenly distributed, kind of among all the sizes, but the scale is definitely not something which is intrinsic to the sizes. We always measure sizes as some number times some scale, kind of centimeter or inch. And if there is some kind of uniform distribution to the sizes, for example, it is natural to assume that the sizes of asteroids in asteroid belt are pretty much random. I mean, of course, it shouldn't be like too huge, it shouldn't be, well, it could be a tiny dust, but it shouldn't be too huge if it is called an asteroid, otherwise it would be a tiny. But still, in this range, it should be kind of evenly distributed. But on the other hand, it should be scale invariant. If you measure the distribution of ones, twos, and so on in one scale to another scale should be the same distribution. It means that if we enlarge all the numbers by a factor of 2, instead of unit of 1 centimeter, we take 2 centimeters, the distribution should be the same. Well, what does it mean? It means that just the logarithms of numbers are evenly distributed. Because, well, what does scale invariance mean about logarithms? It means if you take all the numbers and shift them, changing the scale is multiplying the numbers by a given number. It means shifting the logarithms, adding the constant to all the logarithms. Then the distribution doesn't change. It means a uniform distribution of logarithms.
Wait, I thought the number itself was uniform distribution.
So, no, that's what I'm explaining. What is uniformly distributed is this thing, the whole size.
Yeah.
There is no reason to expect that the sizes of asteroids will be particularly distributed in special ways. The sizes, well, they're pretty much random. But the scale is also pretty much random, because, well, it's up to us what scale we choose. So this distribution, if there is some distribution, it should be scale invariant. It means that logarithm of these numbers, should be evenly distributed. But the question of whether a number starts with a 1 or with 2 or with whatever digits is something about the logarithm of this number. X starts with 1 if, well, what? If x is between 10 to the power k and 2 times 10 to the power k, or logarithm of x to the power to base 10, its fractional part is between 0 and logarithm of 2 to base 10. Which turns out to be 0.3, something like this. On the other hand, the first digit of x is 9. X starts with 9. X is between 9 and 10 to the power k and 10 to the power k plus 1, which means that logarithm of x to the base 10, its fractional part, is between logarithm of 9 to the base 10 and 1. And it turns out that 1 minus logarithm of 9 to the base 10 is about 0.045. So while in any small, large enough table of distributed enough magnitudes, there will be about 30% of numbers that start with 1. There will be only 4.5% of numbers which start with a 9. And it's just, well, this proposition used two facts. Well, first of all, whatever we measure should be measured in some random scale, kind of the result of measurement, the scale is not kind of natural. And yes, it's a good assumption about most of things in physics. I mean, there are quantum tests. We know that some scales are more natural than the others. I mean, there is, I don't know, Planck constant or something like this, which is a natural scale, but on kind of large scale, we don't notice these effects. Pretty much we don't have any natural scales. So in any set of data with this property, which is distributed wide enough, there you will notice this law, this Remford's law.
It's Remford still alive?
No, so it was found in 19th century by Newcomb, and he did in fact, so how many, so number of proportion numbers starting with k is logarithm of k plus 1 minus logarithm of k to the base 10. So that's the law. And Newcomb did find this law, and it was popularized by Cranford. And oh, what's funny, this came up in physics. Well, first of all in astronomy, Newcomb was an astronomer, then in physics, Cranford was a physicist, and eventually went all the way to accounting. So April is the month when they file tax returns, and we have lots of numbers in tax returns. And well, while those numbers are not really distributed in really random ways, there are many more people with kind of lower salaries and people with very huge salaries, but still there is kind of range of distributions. And it's even better, even more evenly distributed in the tax returns of large firms. You have huge amounts of data, huge amounts of actual numbers, and they're all measured in some units, dollars, which are, well, pretty random units. There is no intrinsic meaning to what is $1. So you would expect that if you tabulate all the numbers in a tax return, you will find such distribution. The number of numbers that start with 1 will be about 30%, the number of numbers that start with 9 will be 4.5%. Well, but most people are human and don't go to number theory courses and don't read astronomy journals, and if they take accounts, well, they will make the numbers humanly random, not actually random, but humanly random, which means the distributions of 1 and 9s will be about the same. In fact, well, somehow, for some stupid reason, people would prefer 9 more than 1. That's what they read in accounting journal. So, in 70s, there was the first attempt to apply Cranford's law to actually find tax returns which were fraudulent, that were fake, and yes, it was very successful. And then, in fact, at least in the US, you can use Cranford's law as, without actually pointing to a mistake or to a fraud inside of tax return, you can use Cranford's law to show that it's fake and, well, still affirm that tax return doesn't obey Cranford's law. And of course, it gets more and more complicated. Once you know that a random distribution should obey, you hire accountants which do know that it should obey such a law, and then somebody in the CRA hires other accountants who know even more math, and they check the second digits for proper distribution, which is more subtle and proper. So now probably the largest firms can fake accounts in such a way that it won't be noticeable using the Cranford's law, but still very good, very applicable thing. Okay, so maybe any questions about this? Oh, and basically, powers of 2 naturally obey Cranford's law. You will find much more powers of 2 which start with 1 and powers of 2 which start with 9. You can actually prove it, it's very simple. And powers of any number whose logarithm is irrational will still obey this Cranford's law. And as I said, almost all distributions coming from nature, which are not what's bad about distribution of heights in this room is that there is very small variation. It's 180 plus minus 20, 40 centimeters every corner, something like this. But still, it's very small distribution. If it was distributed over several orders of magnitude, it would obey also Cranford's law. Okay, so any questions? Okay, so take the cookies and see you next